All right, so I'm going to talk about harmonics from solids, and the title is nonlinear all the way because you'll see that there are many ways that solids can make harmonics, and so that is why nonlinear all the way. So the outline, here we go, and actually let me see, pointer. Okay, so the outline is the following. I'm going to go through the basics of harmonic generation from an experimental perspective. So what happens, how you deal with them, and so on. Also, what are the typical experimental parameters to give you, to put you in the mindset of what really we're talking about compared to what you may be more used to, which is gas phase harmonic emission. And then I'm going to go through the emission mechanisms and maybe add a little bit of a real space perspective, also reciprocal space, which is how solids are mostly described in. Move on to one of the topics that I've worked most extensively, which is the experimental evidence of a collision-based emission. You'll know what this is about later. Finally, go through the applications of what we can do with harmonic in solids before moving on to a larger chunk of the talk, which is focused on nanostructure solids and why they're useful and what are the cool things we can do with them, and eventually conclude. All right, so a classical perspective on gas phase harmonics, and probably all of you are familiar with this, but essentially the process of harmonic from gases, it's kind of well understood, at least the basics of it. And it starts essentially with an atom which sits in a gas, so it's quite lonely. It's completely independent from any other atom nearby, which obviously are far away. And when the laser field is strong, this atom undergoes tunnel ionization, or the electron is tunnel ionized, or by whatever other mechanism is ionized. Eventually, goes from a bound state to a continuum, which is also a rather boring continuum. It's just a vacuum whose the electron energies scale quadratically with the momentum. And anyways, the laser field accelerates in this continuum. It brings it away from the atom. And then when it changes sign, it sort of comes back and slams the electron onto the core with very high kinetic energy. And this kinetic energy can approach kiloelectron volts nowadays. Once the electron passes by the atom, there is a quantum interference between the electron and the part of the electron that stayed instead back into the bound state, and this interference leads to an oscillating dipole, and that emits harmonics. Or in other words, this electron can recombine with the ground state and emit a photon. So this is basically harmonic generation from gas phases. And of course, a lot more nuances than this. It's truly a quantum mechanical process, and oftentimes we make use of this quantumness of harmonic emission. But what happens if instead I put other atoms nearby? And this is basically like a solid. And in fact, what I picture here schematically, obviously in this cartoon, is not even a perfect solid. It's a solid possibly in a somewhat real condition. Of course, this is dramatic, but something which isn't exactly periodic, and maybe there are some oscillations and vibrations in it which breaks this periodicity. And there are also, of course, ions, the big balls, and then smaller circles, the red ones. Those are all these other electrons which are sitting in the solid. And you could ask yourself, what happens now when any one of these atoms is ionized? And I say anyone because, at least in the perfect case, every atom is identical. Possibly not so much in this case where there is a phonon involved, but let's say every atom is identical, so any one of them can ionize. And of course, you could say, well, the electrons which are bound are going to find themselves in a continuum, which in this case is not a boring continuum because there are other atoms nearby, and so there will be interferences and such. And is also, because it's in a continuum, it can also be accelerated because the mass will be not infinite, like in a bound state. It will be accelerated, and during the motion, it will feel all the other atoms. We'll feel the other atoms, which is the lattice. We'll feel other electrons schematically here with an electron bouncing off another electron, and those are scattering events, dephasing, and so on and so forth. So all this happens while the electron moves, but eventually it's gonna also revisit the atom from which it started, and something else can happen. There's maybe some other type of collision and so on. So it's a richer environment to drive strong field nonlinearities. And this is what I hope to convince you about. And so let's delve into it and see what really happens in a solid as we know it, as far as you know it nowadays, which is, we made a lot of progress, but we're still at the early days, I would say. And I said, yes, it's 10 years of solid harmonics. The first experiments was done in Stanford in the group of David Rees in 2011, but it wasn't really until about 2015 that things start picking up in this field. So it's 10 years on paper. In practice, it's been a little less than that, and there is a lot more that can be done. I show here the very first spectrum that was measured from so David and Shambugimir, who was the lead author on the paper, used the 3.2 micron laser with a very moderate field strength compared to what you're used to in gases, which is about terawatts per square centimeter. And they focused tightly on a 0.5 millimeter thick zinc oxide single crystal. Now, zinc oxide is a semiconductor, the band gap is about 3.2 eV. And so if you compare it to the typical ionization potential of atoms, it is much, much less. And so that's kind of why you can't really drive semiconductors with 800 nanometer light, because you incur 2-photon absorption or 3-photon absorption, and that's very inefficient. I mean, it's very efficient, and that's the problem. You can't really put a high field. So that's the reason for going to very long wavelength. You can more easily apply a strong field to it, which means high accelerations without incurring too much ionization and eventual breakdown. Okay, so when they put this on zinc oxide, this is the spectra they see at 2 different field strengths, and you can see essentially a large background. In this case, was due to fluorescence, which is typical when you use thick crystals. Fluorescence at the 3 eV band gap, and then all these other harmonic peaks plus some other stuff in between, extending all the way up to about 10 electron volts, which isn't much compared to hundreds of electron volts which you're used to in gases. But of course, the deal here is the physics underlying the emission. And there was a recent review article also by Shambhu and David published in Nature Physics, where they sort of put together a summary of experimental measurements of harmonics from all these different crystals. And you can see some trends. For example, if you're looking at dielectrics such as glass, magnesium oxide is also a very good emitter of XUV. Band gap is about 8 or 9 eV, something like that. Sapphire or quartz, and even solid rare gases, solid argon and solid krypton. These are all characterized by large band gaps, and they tend to emit the highest photon energies with, right nowadays about 20, 30 electron volts, I would say, is what's been demonstrated. And also they tend to be pumped with 800 nanometer or near infrared lasers, and the reason for this is because thanks to the high band gap, you can use a shorter wavelength. And then there is all the other semiconductors, the wide band gap semiconductors such as zinc oxide, or other semiconductors such as silicon, or even two-dimensional materials such as molybdenum, the sulfide, and even semi-metal like graphene. And recently, here in Ottawa, we've also been working on other metals such as titanium nitride and so on. So it's getting richer, and these tend to be emitting in the visible to vacuum ultraviolet up to about 10 eV. That would be zinc oxide, and they tend to be pumped also with longer wavelength drivers. The reason, again, is that if the bandgap is small, you want to stay away from 2-photon absorption, so that pushes your driving wavelength further in the infrared. So this is basically state-of-the-art. And the first question you can ask yourself, okay, I have a crystal, and the crystal is essentially a periodic arrangement of atoms. It's a lattice. And what happens? Does it really fill the lattice? Because this is really a difference between gas phase harmonics, where you have an atom sitting lonely in the vacuum and nothing else nearby. And the answer is yes, of course. It fills the lattice. Everything, we're driving these currents inside the crystal, and yes, it does fill the lattice. The very first demonstration also was back with the first paper on zinc oxide, where they took a zinc oxide crystal cut C-axis cut or A-axis cut. Something like this. Essentially, they had zinc oxide is an hexagonal crystal, and I show here the structure where the C-axis, which is the long axis, the birefringent axis, is in the plane of the surface, horizontal, and then the other axis is the other direction in the plane of in the surface. So this gives the strongest anisotropicity because the hexagonal planes are actually perpendicular to it, and so you don't probe this. You really probe a twofold symmetry, c-axis or perpendicular to it. And you can see the harmonic spectrum as it varies very strongly when you every 90 degrees, and that's again the this fourfold symmetry. Whether you're aligned along the c-axis or perpendicular to it, you get very different harmonics, harmonic spectrum. So clearly the electrons probe the lattice symmetry, and in fact it was demonstrated, in fact you would imagine it probes the periodic potential, and it was very recently in the group of Giulio Vampa that they were able to reconstruct or map out the electrostatic potential in a magnesium fluoride crystal, and with picometer accuracy, because those are the size. Angstrom is the size of unit cells in crystals. Now, following the work on zinc oxide, there have been other demonstrations of how sensitive it is to the crystal orientation. Most notably, if you go into the XUV, you take a magnesium oxide crystal, thinner in this case, 200 micron. It's a cubic crystal, as you can see here. Cube crystal has this arrangement of magnesium and oxygen in the 001 plane, which is basically a cut of the surface of the cube. And you can see here, as you rotate the crystal or the linear polarization with respect to the crystal, you get this very sharp maxima at 0, 45, 90, 45. And they sort of have a similar features. The 0, 90, and 180 and 270 are very narrow, whereas the ones at 45 are sort of broader. And there is a connection in the sense that when you have 0 and 90, if you start from oxygen, which I believe is what the valence band of oxygen is made of, we'll talk about it later, and you drive it up and down or horizontally, the next atom is magnesium, and so you go from oxygen, magnesium, oxygen, and again oxygen, magnesium, oxygen. Whereas at 45, you sort of connect the same species, so oxygen, oxygen, oxygen. So you would expect a different behavior, and in fact, there is a difference in the amplitude and the width of these peaks. So clearly has this sensitivity. More demonstrations. This was for my own work in silicon, which now has the diamond structure, and you could see as you rotate. Maybe this isn't too clear, but nonetheless, as you rotate, you see that there's again a sensitivity to the crystal orientation. This is fourfold. Now silicon, it was pumped by a 3.5 micron laser, and although it is an indirect bandgap material, as many of you probably know, the indirect bandgap is about 1.1 V, but the direct bandgap is actually 3 V, and that's what we make use in high field science. Finally, one more demonstration. This is also recently taken in my lab. By no means we are the first to do a molybdenum disulfide. David Rees also did this first. It's again the orientation dependence of a molybdenum disulfide crystal. This is a two-dimensional van der Waals crystal in the monolayer limit. And you can see this beautiful pattern, six-fold patterns, and also some interesting features where some harmonics have a maximum or other have a minimum. So definitely feels the periodic potential. So the potential matters, but now the questions I want to answer for you is, how do electrons really move in crystals when you add strong fields to them? And I find it useful to put a few numbers down to estimate, okay, what are the length scales involved in high field physics in solids? And one of the lengths that you're probably used to is the Pondermotive radius, which basically tells how far the electron goes away or travels from the ion. In isolated atoms, assuming standard parameters 10 to the 14 watts per square centimeter and 800 nanometer wavelength, you end up with a 17 angstrom separation. Now, if you take a crystal as 100 times, such as zinc oxide, at 100 times less intensity, but at a much longer wavelength, and the mass of the electron, turns out, you'll see later, is actually a third of the mass of the electron in vacuum, because this electron moves in a solid and sort of is dressed by the lattice, and it actually feels lighter. end up with 170 angstroms, which is huge. This is actually, in zinc oxide, it's about 35 unit cells. So what I depict here is actually very conservative. This electron actually travels a lot further than just 2 atoms. And that opens a whole set of opportunities, which maybe I'll get to talk it later. Now, this is my crash course of solid state physics 101. But maybe I'll skip, I'll go quickly over this, as this is probably the most boring part. So solid water characterized, of course, by an Hamiltonian, and this Hamiltonian is periodic because there is discrete translational symmetry, because you have an atom here, an atom here, and an atom here, and all these atoms are equal. And they're periodic with this capital R, which is basically the reciprocal lattice vector. As a result of this periodicity, you can read about Bloch's theorem, but turns out that the eigenstates of these Hamiltonian are the so-called Bloch eigenfunction, Bloch waves, which is psi n k. So they're labeled by an index n, which is the band index, and a momentum k, which is the crystal momentum. And the properties of these wave functions is that this crystal momentum is conserved, this k, essentially. That's what really matters. And they're constructed in a way that have this form, basically a plane wave with this crystal momentum k multiplied by this wave function with function u, which is periodic with the period of the unit cell. So this is basically the function that defines how does the wave function look on each atomic site. And then on top of this, and this is periodic, it's every atom has the same. And then on top of this, there is long modulation, which is this plane wave component, which essentially tells you how this electron travels. And the result of this also, the eigenvalues are also periodic. So if you go to a reciprocal lattice vector away, you get the same wave function. And that's basically what I'm showing here. If you can construct a solid just by taking a solid in vacuum, and you'll get this parabola, k square over 2, that will be the dispersion of vacuum. And just by adding the periodicity of the crystal, you get basically folding. That at some point, when the electron acquires sufficient momentum, its wavelength matches the distance between 2 neighboring atoms, and the back reflected wave causes it to the backscatter from the other atom causes it to back reflect, and causes basically a standing wave, and then it starts moving back if you increase that. And essentially, in the end, what you end up is a folding of your dispersion into what's called this width would be 1 Brillouin zone, for example. And each branch of this is a band. You can also construct it basically, and so in this case, I show here 3 bands. The first band, then it reaches the edge of the Brillouin zone, it folds back, will be the second band, and then eventually there will be a third band up here. You can also sort of naively construct these bands by considering one atom and then taking a second atom and another atom and then bringing them close together. And then what happens is the wave function of each of these atoms, when they start talking to each other, they have to sort of hybridize, and essentially instead of having n discrete levels, all degenerate, you end up having split levels, splittings, and so on. And if you have many atoms, all these splittings basically blur out in actual bands. This is why you have bands, essentially. And this is how this wave function looks like, essentially. That's what I said before. You have this periodic part, which would be this double maximum wave function, so to speak, which is modulated by this longer periodicity. Now, the key aspect here, it's a coherent addition of all electrons on all lattice sides. So I mean, this is a really solid state physics 101, but a perfect crystal does not scatter. It's not like because you have an atom there, the electron moves and scatters off this atom, because the very fact that the electron isn't that wave function, it already includes the effect of the potential. What can scatter is impurities or imperfections, such as phonons, where the atoms are not exactly periodically spaced, but some are closer together and some are further apart. Other electrons or impurities, so missing atoms or dislocation and things like this. This is what scatters. It's not the existence of the potential itself. And also this, what I've presented to you is a reciprocal space perspective, and the reason is that the true wave function, the true eigenstates of the Hamiltonian are the block states, but you can transform it and get a real space perspective, whereas in which the wave function are not completely delocalized, like in this case, like in the block state, but they're really maximally localized on each side. And these are called Vanier states. And there's been work lately here in Ottawa on reformulating harmonics in the real space, and that can give a lot of insight into what happens, because we are sort of tend to think in real space, especially people in attosecond science. And address this representation is more used to address issues such as, how localized is the wave packet, what's the role of adjacent sites, and so on. And there are also other methods, density functional theory, and so on and so forth. Now, what are the electrons truly delocalized, though? I mean, I said that you have one block function and it's completely delocalized, but really not, it isn't. And the reason is whenever you excite the system, you create a wave packet. So you create a superposition of the block wave with a certain amplitude. And just like in an ordinary laser pulse, you can rewrite this and factor out a plane wave component, and whatever you're left with is the actual wave packet. And so here is a calculation of what a strong field ionized wave packet in hexagonal boron nitride looks like. Mind you, this is a calculation. You have never actually measured this. So we think this is what it is, but we really don't know. And you can see, it spends about 10 unit cells, and you can see that it's the density is only on the lattice sides as required, or in between the lattice sides if you're going through a different bands. And then on top of this, there is this long modulation. So it's essentially like a free space wave function, but sampled only at the lattice sides. Now, I said you can take this and in optics, if you have a laser pulse, you construct it by adding waves with a certain amplitude. It's essentially the same procedure. In the factorization, what you're left is a wave packet that moves at a certain speed, which is the group velocity. It comes out of the math. And so the analogy between the two is in optics, the phase velocity is given by the wave vector that you factor out of the plane wave component, and the same is for the crystal. In a similar way, it's omega over the wave vector, just like in optics. The group velocity of the wave packet is the derivative of the momentum with respect to frequency, which comes in here. And in a solid, that also is how the velocity of the electron of the wave packet, which in this case turns out to be the derivative of the energy over h bar, which again is frequency over k, delta k. And you can take the analogy further if you consider higher order dispersion, the GVD or the group velocity dispersion of the wave packet in optics turns out to be related to the effective mass or the curvature of the bands, and so determines what the mass of the electron is. And so because of this, if you can consider, for example, the band energy cosine simple formula goes like this. The velocity of the wave packet of the electron into these bands is the derivative of this. So it's basically a sine function. It's positive when the crystal momentum is positive, and it goes negative when crystal momentum is negative. But it doesn't go on indefinite like in free space. Eventually, it caps off and it decreases. And this is the effect of the lattice. The fact that when you are approaching a certain momentum, the backscatter from the neighboring sides creates an interfering wave that travels the opposite way. And at some point, the interference is maximum, creates a standing wave, and then the electron won't move anymore. And that's when you reach the edge of the Brillouin zone. Okay, now, all you need to know how electrons move in solids is really these two equations of motions: how the wave packet moves, the speed, and how the momentum changes. And that is given just by classical physics by the electric field directly and the magnetic field, which we'll not consider in this case. Now, that's not truly complete. There is also another effect, which is called Berry curvature, that adds into the velocity, and we'll give you a glimpse of what that does later on. So that's all we need to know. Essentially, if you apply a certain electric field look at this in momentum space, you start with an electron at zero momentum. That momentum is going to change just because you are applying an electric field according to this equation. So the electron essentially climbs up the band. And in real space, what it does, you take is essentially given by the first equation. When the electron has gone to this momentum, it's going to have this velocity, which is the gradient of the bands. And so that sums it up essentially. One of the possible things that happens in harmonic generation is you start from a valence band, which has a certain dispersion, and you tunnel ionize step 1 to a conduction band. That's the red one again. And then the field is applied, the field is still strong, so it accelerates the electron, it gains energy and momentum, and then at some point in real space, it's going to encounter the hole that was left behind in the valence band. And there you can have an interference between the two and a possible recombination. And that is certainly one way that harmonics are emitted. This is sort of a generalization of the 3-step model of gas phase harmonic emission to solids. Now here is a movie that shows you exactly what happens in magnesium oxide, which is a emitter of XUV light up to about 20 eV. So in this plot, you'll see the position of the let me see. All right, so this is for a gas. So the red is the conduction electron. In this case, will be just electron in vacuum. And the blue will be the position of the valence electron, which in this case is stuck on the ion, which is infinitely massive, so it won't move from here. And the black is the laser field. And then in this here, you'll see what the momentum of the electron hole pair is, or in this case, the electron really is as a function of time. We will see this swinging back and forth according to the laser field strength. And then here I'll show you the energy that the electron has at recollision as a function of the birth time. And you should all know this. How do I bet. Okay, hold on a second. There you go. There you go. So as time goes on, oh, this is a function of birth time. You'll see that these trajectories, and as soon as you approach the electrons ionize at the peak of the field, you see they recollide at the next cycle, as you know, and then as the birth time goes on, increases, the recollision time decreases. And you'll see that the photon energy emitted goes up and then goes down, and you have your short and long trajectories, just like you know in gas phase, and this is the gas phase result. Now let's look at MGO instead. This is a lot richer. For example, the valence electron, the hole also moves because it's not now, it's in a dispersive band. And again, about the peak of the field, the electron hole recombine, and you can see the energy climbs up, and so does the momentum, reaches all the way up to the edge of the Brillouin zone, and then comes down again. And so it looks very similar. You have two branches, and the maximum, that would be the cutoff. It would be short trajectories or long trajectories. But it is not just a generalization of, it's not the same as in the gas phase. So first of all, the electron can collide with the hole, and it also propagates in a continuum, the conduction band and the valence band, which is structure, is not just a boring dispersion of vacuum. So this leads to some sort of generalized trajectories, which you can't just normalize to 3.17 UP, which is the cutoff of gas phase harmonics. Also note, as a side, that, for example, there are differences other from the fact that all the energies and recollisions are different, but the recollision can happen away from the origin. Perhaps you noted that sometimes the two curves crossed away from zero. And pairs, in this case, for example, if you ionize before the peak of the field, you could have recollisions before the peak of the field, which is not something you see unless if you had Coulomb attraction in gases, and of course the cutoff saturate, and that is because if in a two-band model the maximum energy allowed for recombination is just the gap, the maximum gap you can get. So higher harmonics you can get them, but requires extension to higher bands, and that has been observed in rare gas solids. For example, this is what is it, argon, solid argon, where they saw sort of a first plateau and then a second plateau, and they said, oh, these harmonics actually coming from a higher band. And was also observed more recently in magnesium oxide, where you would see these peaks at much higher energy than the first gap. So at 17 eV would be the maximum gap between the first valence and the first conduction band of MGO, and then these are higher lying conduction bands. And then you would see these harmonics here where the density of state is high, and also that also shows that it depends clearly on the density of state. Now, what is interesting though is that harmonics emission from solids, and this is why they're no linear all the way, has a lot more richness than gas phase. There are other ways you can make harmonics. And for example, one of the mechanisms that has been studied the most is this anharmonic motion, or it's called block. People call them block harmonics, and this is it basically is the following. You can see that the motion of these electrons is not sinusoidal, like it would be in the gas phase. In fact, because it moves in these bands, which are not parabolic, you can see they're pretty flat here. They're pretty straight. Because they move in these bands, their motion has an harmonic content. It's a structure continuum, so you get a structure motion, and because this is non-sinusoidal, it has a harmonic content. You have an oscillating dipole that doesn't just do back and forth harmonically, but it's very anharmonic, and so that leads off harmonic. And people call these block harmonics. Sometimes I call them velocity harmonics. And so that's one motion, one reason. There are other mechanisms too. For example, the very fact that you ionize, it means that you're increasing the current every stepwise every half cycle. And this is basically what I show in this simulation, where at every peak of the field, the conduction band population sort of jumps up and then jumps up and then jumps up again. And that also is a nonlinear increase in the current density. And that also leads harmonic. These are called Brunel harmonics from François Brunel, who was an old, sorry, I shouldn't say that. Back in the days, he predicted this at the NRC a long time ago, and so these have been also somewhat observed in the group by Baltushka, and even more recently there was another demonstration where they actually look at what happens as the electron tunnels out of the barrier, and what they found is that the contribution to the current mostly comes not from the Brunel contribution in their case, which is the real current. So once the electron is born into the continuum, then there is a jumping current. But it happens as the electron tunnels. And you can imagine that it sort of squeezes through the tunnel. And so the current density there is clearly pretty high. And that's what they demonstrated. And they call it this under the barrier current, sort of like arises from the complex nature of it. Of course, it's quantum mechanical, called the injection current anyways. So these are already three sources of harmonics plus recollision 4, and there is another one that we looked at in the past where instead of having recollision, you have a cascaded block oscillations. I won't get into the details, but that's yet another source of harmonics. So, you could probably come up with your own source if you really think hard enough. Now, I'll switch gear now. Well, I'm sorry, not switch gear, but I'm going to talk a little bit about this recollision, which is some of what I've done the most. It's being very similar to high harmonics from gases. You can appreciate that each harmonic is emitted at a certain time, like when the electron and the hole recollide with that kinetic energy. And so just like in the gas phase, there is this chirp of the harmonic emission where the photon energy increases versus time. There is this, you establish these trajectories which are completely determined once you know the energy of the harmonic, and that will also tell you what the time of recollision is and the time of birth of that trajectory is. So it's all linked together. In the velocity model, or what people also call block harmonics, instead, it's a purely classical phenomenon. So, and it's symmetric in time, so there is no phase, and so all the harmonics are emitted simultaneously. And this is a simulation of this. So this, in principle, is a very good way to discriminate the two. And in fact, the group of Giulio Vampa did this in the past, where they look at the group delay emission of harmonics from glass or quartz, and they saw, in fact, that they weren't delayed, and they concluded that, at least in gas, the block harmonics were the dominant source of harmonics. I've worked on a different crystals. I work on zinc oxide and a few others, and I basically found evidence for collisions, and the way we did it is to control the emission process in situ. So as the harmonics are generated, you perturb it just ever so slightly, and that gives you information about the timing of these trajectories, or you can sort of tag these trajectories to each harmonic. And the method is this two-color bichromatic fields, linearly polarized, and with parallel polarizations. When you add a second harmonic to a strong fundamental field, that's the blue over the red, over the black, you create an asymmetric field. And just by doing that, you would expect that even harmonics pop up, because now the field is asymmetric, and you drive this often on a symmetric crystal. So you end up having even harmonics. But the crucial thing is that you can control the degree of asymmetry. You can delay one color with respect to the other, and thereby you sort of maximize the symmetry seen only by one trajectory, because each trajectory is born and is terminated in a certain window of time. So if you make the symmetry the highest in that window, that harmonic will be, that even harmonic associated to that trajectory will be the highest one compared to the others. And you can delay the phase, and so you can pick different trajectories. And so what you expect to see is that the different even harmonics are maximized for a different structure of the field at different phases. And that's exactly what we see in zinc oxide. These are showing harmonics 6 to 18. And you can see the even harmonics here. As you change the delay between the two colors, here I linked the minima. The minima varies with the delay. And you can estimate what this variation is for a recollision model in zinc oxide, and sort of agrees pretty well. And since we have done this in silicon as well, similar features, we've done this in the XUV from magnesium oxide, and again, similar features. Here I'll show this, where again, so 12 to 18th harmonic, this is about 20 V, where this optimum phase where this harmonic is maximum varies with the harmonic order. So this is basically a survey of the take-home message is different crystals in different regimes may have different reasons for emitting harmonics. And this is very much an open debate right now of understanding why do some do this and others don't. Now, this is instead my one slide onto the role of Barry curvature. So if you go back to the equations of motion, you remember that the velocity of the electron or its wave packet is the gradient of the band. So that's completely determined, but there is an extra term which is this Barry curvature, and it's a property of non-heterosymmetric crystals, geometrical essentially, and but essentially what it does is, being it the cross product with the electric field, it adds a transverse kick. You pull the electron this way. In this case is along X, pull the electron along X here, but it actually starts moving along Y. And this is what, this is basically a Hall current, if you know what that is, an anomalous Hall current because there is no magnetic field. It's the Barry curvature which acts as a magnetic field. Just to give a feel, for example, this is a sample trajectory in MOS2. You pull it X, but look at what it does. It has this very complicated trajectory that sort of circles the electron and the hole around. And so this opens a whole lot of opportunities to try to control or measure Barry phase by sort of measuring these trajectories. Now, my second part of the talk, maybe go just quickly over this. What is harmonics good for from solids? And I show 3 examples of what we have done, and leave to your imaginations what else can be done. But essentially having these trajectories or being able to steer these electrons throughout the whole Brillouin zone and to very large length in real space allows us to coherently probe the underlying structure of the material. And so I'm going to show you band structure, Barry curvature, and how to measure electric fields. Now, measuring band structure is kind of simple once you understand how harmonic works. As you tunnel ionize, you're swinging these electrons back and forth, and they sort of integrate all the effect of the energy dispersion. And they give off this energy back into the photon when they recombine. And this is basically the dipole phase that you know from gas phase harmonics. It encodes the dispersion of the material. And so by tagging these trajectories, you can back out what the dispersion was throughout the K-space. And I've chosen to do this with, again, 2 color fields by sort of matching this variation of the even harmonic maxima, this optimum phase, with the harmonic order, which I've shown you for zinc oxide, to reconstruct what the dispersion of the zinc oxide bands is. And you can see the target phase and the retrieve phase for these bands match very well. So we were able to sort of predict that the harmonic, the band structure of zinc oxide, given this harmonic dispersion, was exactly the one that you would simulate. And this was theory. We had done some preliminary experiment in zinc oxide again, up to about a few harmonics, and we could see that the dispersion agreed with tunneling from only one of the valence bands. You have 3 valence bands in zinc oxide, and the one with the highest curvature, which is the split-off band, which is also the one with the lightest mass, because the curvature is the one that tunnel ionized the most, and that also agrees with what you would expect. Opens the way. It's complementary to Angler's law of photoemission spectroscopy, because you can do this on insulators. You can measure potential electron phonon couplings, which is a kind of a holy grail. And well, the last one we'll skip. Now, the probing barrier curvature, it was sort of, there is a preliminary experiment also in the group of Giulio Vampa, where they would use this intra-band harmonics and their polarization and intensity scaling, I believe, to back out what this barrier curvature along one direction in the reciprocal space looks like. And so these are, again, very interesting results. Finally, you can sense all sort of things. You can sense electric fields, which is kind of useful to map out, to image live electric circuits in semiconductor devices. Here we have done, well, you know what, I'm going to skip this. I'm just going to show you the result. Essentially, you can apply a DC field on it. You can get even harmonics because the DC field breaks the symmetry. And by looking at even harmonics, you can get the structure of the electric field. In this case, micron resolution, but there are ways that we can extend this to the nanoscale. And of course, you could do it with space charge, but I really want to go now to the last part of my talk, because I think my time is about to run out. Nanoscale control of high harmonics. And I believe this is a great way to sort of merge with other fields of science which weren't touched by Attoseconds whatsoever, and sort of gives us an idea of what we could do towards Attosecond technology. Now, nanostructured surfaces have been used. There is some work, very exciting work, and it's really at the early stages, and is a collection of all the work that's been done. But generally, it was, people look at it in 2 approaches. One was to use nanostructured surfaces to boost the efficiency of harmonic emission, and the other one is the latest work that we did, which was a way to beat absorption of the high harmonics. In boosting the linear interaction, essentially meant that you can design nanostructured surfaces to enhance the driving field strength. And you can do this with resonant plasmonic antennas, which is part of the work I've done in the past. These are gold antennas on silicon, and they're designed to resonate at 2 micron, which is the driving wavelength. And you can see a plot of the enhancement. These are plasmonic antennas, 5 nanometer inside the silicon. You have this huge enhancement of the intensity on the edges of the antennas. And that's where high harmonics will preferentially take place. What we have seen is that when you illuminate the antennas with the right polarization, you get this 10-fold enhancement of the flux. So clearly they work, and we estimated that the harmonic emission region to be as small as 20 by 20 square nanometer, which is really tiny. And there is work currently being done in my group to build upon these results. Here's another example. Instead of using plasmonic antennas, we use an all-dielectric metasurface, but it's a phonoresonant metasurface as a complicated behavior, which I don't have time to go into. But again, you design it to have a certain resonance. It leads to a localized or enhanced field, and that field, I'm gonna skip again all this, gives you, again, a significant enhancement of the harmonic power for a given intensity that you put in. So this is all good, and but really the deal, one of the latest achievements was this beating absorption of the high harmonics, and this is a different approach. In this case, we did not really structure the infrared field. We tried to extract harmonics more efficiently from the material. The problem here is absorption, and the harmonics that we normally care about are those emitted above the gap of the material. And those clearly are strongly reabsorbed by the material itself. And so, just to put it in perspective, we have 10 nanometers useful, because that's sort of the typical absorption length of crystals, but we have microns of material, and all that microns long is completely wasted. We don't get harmonics out of it. So we structure the material in these very thin ridges, and the idea is that these thin ridges are so small that the infrared field is uniformly spread out. It's really strong, even on the interface with the vacuum between the two ridges. And so harmonic are emitted from the sidewall, coupling to the slot between the two, and then propagating the vacuum channel, with experiencing minimal losses. And just to get to the point of it, these are the structure we designed. Are essentially here. An SM image of them, and we couple in light from here. And essentially at the output, we sort of look at the harmonic flux as a function of the width of the slots. And as we increase the slots, you can see these strong modulations of each harmonic, and each harmonic modulates independently, which is a strong indication that we're not really changing the infrared field, because otherwise all the harmonics would modulate simultaneously. What we're really doing is changing the propagation properties of the slot, or the extraction of that. And that's what we demonstrated. Now, if we change the length of the structure, we basically etch them down different height. What we see is that for increasing guiding distance, the harmonic power monotonically increases up to about 700 nanometer, which is what you would expect from building up a propagating distance. Now, 700 nanometer is a 100-fold increase of the extraction depth, because the absorption length of bulk silicon is 7 nanometer. So this is our main result. I believe it's kind of a big deal. And as a result of it, of course, the structure also outperform in terms of power the bulk at all powers, all the way up to the diameter threshold. So that's kind of that was the motivation behind this project, because in all these enhancement nanostructures, to enhance the field, you necessarily have to confine it to small volumes, and confining to small volumes, you lose emitters. So eventually, it is possible that if you had a larger area and enough power, you would still gain by using unstructured samples. But it is not the case anymore. We sort of demonstrated that if you pump it hard enough, that with these nanostructure gradients, you can do actually better than gases. So to conclude, because I think I'm out of time, solids exhibit a rich phenomenology, and we actually barely scratched the surface. Most of us have taken the approach of coming from high field science into solid state. And so we are just about to delve into all the rich physics of solids, which include phase transitions, order. You can have aligned electric or magnetic dipoles. You can have, of course, magnetism, but you can have also ferromagnetism and so on and so forth. And then all these particles can correlate. You can have mod insulators, all sort of correlated behavior, and of course topology, which is characterized by barrier curvature. And on top of that, they're inhomogeneous. You can have interfaces and boundaries, and you can use heterostructures and surfaces to control harmonic emission. And I've shown you can also use nanoscale patterning. So really, I think solids open the floodgate for studying strong interactions in many new systems, and liquids have already started working in liquids. So it's not just a twist of attoscience, or you can do the same things, but in a solid, I think you can actually do new things. And eventually, you will be able to augment the gas phase research with the solids by joining them together. The last few slides, just a advertisement. So we're actually recruiting. There is a position for an NRC postdoctoral fellow, which is going to be tasked with looking at 2D materials and heterostructures, which is kind of a strength that we have in Ottawa. And there are also other positions and other topics. So if you're interested at all, you can catch me at the poster session or drop me an email. Also, don't miss this talk, which is organized by the OSA technical group on Attosecond science, harmonic sources for material development and metrology in the semiconductor industry. So the speakers are Henry Captain and John Peterson from IMEC, which is a leading semiconductor manufacturer. And they've just set up a lab with KM Labs machines to do imaging at the nanoscale that is of interest to the semiconductor industry. So it will be really useful to know. It will be really interesting to know how attoseconds are making it into a technology that we all really much care about. This is my acknowledgements. some of this work was done at Stanford in the last 4 years or so, and now I'm back in Ottawa, and this is a list of my collaborators, and that is it. Thanks for your attention.